Hello everyone, we're back for some more Stat 100. This time I'm going to talk about section 9.3 of the textbook, which is a large sample test about a population mean. So this is the details that weren't really covered in the previous section. We're going to look at exactly how the test works and take a look at a few examples of the hypothesis testing. So in particular, the situation we're going to look at is continuous, and that means measuring as opposed to counting. So there is a population mean, mu, and a population standard deviation, sigma, neither of which we really know. We don't know what mu is and we don't know what sigma is. And our goal here is to answer questions about mu. What can we say about the population mean mu? And we're going to do that by looking at hypothesis testing. And so the particular hypothesis test that we're going to look at right now, the alternative hypothesis, is that mu is greater than some particular value mu sub 0. So mu is greater than some particular value mu sub 0. Mu sub 0, maybe I should fix this greater than symbol. It doesn't look that hot. Okay, oops, there we go. There we go. So mu is greater than mu sub 0. Mu sub 0 is some number. So it's not a variable, it's a number. And in our previous example, we had mu sub 0 was equal to 14, which was the average wage that we were looking at. So in every example we're going to look at, in every problem you're going to do on this topic, mu sub 0 is going to be an actual number, and you've got to read the problem statement to figure out what that number is. The reason I'm writing it as with a symbol is so that we can write down a general rule for how to do the test. In the previous section, we just used a particular example, and in order to kind of smooth the explanation, I'm going to generalize that and just give you a blanket statement about how to do the hypothesis testing for any number. And for me to do that, I've got to assign a letter to that number. This is just communication. On the other hand, mu is an unknown to us. So it's really a variable. It's unknown. It's something we have to, we're going to try to infer information about, but it's still, as far as we're concerned, it's a variable. But mu sub 0 is a fixed value. Okay, so that's the situation for the alternative hypothesis. We're going to look at this one in particular, and then we're going to branch out from there. But we're going to look right now at the one-tailed test, hypothesis test, and that's got a greater than symbol. Now, our null hypothesis has always got to be of this form: mu is equal to something. So that same number, it's going to be the same number in both cases. This is just an example, right? And in any particular problem, you've got to hunt through the problem and figure out what that number is. But in general, we're going to leave it as a letter just so that I can write down a blanket statement about how to do this hypothesis testing. So the same deal as with the alternative hypothesis. Okay, so there's our hypotheses. Notice that this is an exact value. So it says something more than h sub a. it's a stronger statement, stronger kind of statement than the alternative hypothesis. The alternative hypothesis is kind of vague about what the value of mu is. It just says that mu is greater than something. So it could be 100, it could be 1,000,000. It doesn't really say. But this gives a very exact value for the value for the parameter mu, for the population mean mu. It gives an exact value for mu, and so it's a kind of a stronger statement than the alternative hypothesis. And that kind of gives us a bit of leverage. That's why we work with the null hypothesis. We prefer to work with the null hypothesis because it's a stronger statement and it's easier to contradict it. So it's easier to prove h sub 0 is wrong, to reject h sub 0, than it would be to prove that h sub a is right because of the strength of the statement. All right, so those are just some things that I'm trying to flag for you. Now we're going to use the central limit theorem on this thing. So we take a sample. The sample size is n, as usual. The sample mean is x bar, and the sample standard deviation is s. So these are all the usual letters for talking about a sample. Now, we are interested in establishing a contradiction or a kind of a contradiction, as I explained last time. So what we're going to do is assume h sub 0 is true. And so that is that mu is equal to some number. And then we are going to use the central limit theorem, etc., some mathematics to show that some number, the z is too large. Oops. Right, so that some number z is the test statistic. All right, so this is what we hope to do. Maybe we're not going to succeed at it, but our general plan is that first we assume the null hypothesis is true. Then we're going to use the math that we know, the central limit theorem and so on, to show that the test statistic z is too large, that it's improbably large. And from there, we're going to conclude that something is wrong with our assumptions. And the only assumption that we've really made is that h sub 0 is true. So consequently, we reject h sub 0, say it is false. So h sub a is accepted as true. So these words false and true are a bit strong for this situation, and you might say, instead of false, you might say unsupported by the evidence. And true, oops, I should say false. And true, in this case, I'm going to replace with supported by the evidence. So that's really the strategy that we outlined earlier regarding how to proceed with a hypothesis test. Now let's look at all the details of formulas. So the standard error of the sampling distribution is the usual formula. We've studied this in chapter 7 and 8, so it should be pretty familiar to us now. The standard error is S over the square root of n. That's an approximation because really it should be sigma over the square root of n, but we don't know sigma. And the mathematicians have shown that for a large sample, let's just continue with this parenthesis, for a large sample, that sigma is approximately equal to S. So we are going to use the standard error S over the square root of n. All right, and so now, given that information, we can calculate the z-score of our observed value. So the usual formula for the z-score is that we take the observed value, we subtract the actual mean, and this we are hypothesizing that mu sub 0 is the actual mean of the sampling distribution. So that's the hypothesis H sub 0. All right, so this is where we're using the assumption that the null hypothesis is true. That allows us to pin down an exact value for the mean of the sampling distribution. And that's what we use in the formula. So the z-score for our observed value is the observed value minus the mean of the sampling distribution divided by the standard error of the sampling distribution. And I'm just going to fill in what we know about that. So there is our big formula for Z. So this is the test statistic. And so you should calculate the test statistic for this statistical test. Now, we have to answer the question, what is too large? And we do that by establishing the significance level alpha. And we, as usual, have a few common values for alpha. The most common is that alpha is 5%. Other values that we can use are alpha is 1%. Very seldom we use these other two, that alpha is 2% or alpha is 10%. So these are uncommon. These are this is the most common. This is sort of middle. What does the significance level mean? Well, it is the probability. Specifically, it means the probability of rejecting H sub 0 when it is true. Right, so that's precise meaning. We've talked about the significance level before, and in chapter 8, for example, but we haven't really given us a very precise meaning to it until now. So the real meaning of it is the probability of rejecting the null hypothesis when it is true. This is an error. So what we're doing is we're setting a bound on our error. We are controlling this error. So if I find it acceptable to reject the null hypothesis when it is true 5% of the time, then that's what I would use for alpha. And if I found it acceptable to reject the null hypothesis when it is true only 1% of the time, that's what I would use for alpha. And so that I make that decision. I decide what is the acceptable error rate, or the acceptable probability of making an error of this kind. And then with that in mind, I can now make sense of the situation. So let's take alpha to be 1% for this example. And so I'm going to draw my graph. I love this graph, and you would do well to draw it whenever you need to understand one of these situations. And so if alpha is 0.01, then down here there's 99% of my measurements, and up here there's 1% of my measurements. Now you can do a reverse lookup on your Z table. So let's just do that right now. I'm going to try to find 99% in the Z table. 99% is around 2.33. It's pretty close. It's not quite, I mean, you can use interpolation if you want to, but that's too accurate for us. So 2.33 is going to be our Z value here. And so now we're assuming that h sub 0 is true, but if we get a Z value that's in here, around there, there are really two things that can happen. One is that h sub 0 is actually true, and we are rejecting it because it's in this so-called rejection region. And that would be an error. And so you see that error only happens 1% of the time. That's exactly what this means. That's exactly what this diagram means. That we are rejecting the null hypothesis when it is actually true 1% of the time. Otherwise, we are rejecting the null hypothesis when it is false 99% of the time. Okay, so that is how we conduct our statistical test. So we establish the rejection region is given by our significance level. Our significance level determines the critical value, which determines the rejection region. And then the acceptance region is here. So we're gonna define acceptance and rejection regions many times in the rest of this course, and always the acceptance region always contains the number 0. All right, so if our test statistic is 0, we should accept the null hypothesis. That seems to make sense because the sample mean and the assumed mean, the hypothesized mean, are in agreement. If our test statistic is 0, they're the same. There's absolutely no reason to reject the null hypothesis in that case. So 0 should always be in the acceptance region. So that's just something to help you, a little mnemonic, a little memory aid to help you find the acceptance region in these diagrams that we're going to be drawing. The acceptance region always contains 0. The rejection region is everything else. All right, so that is a more detailed outline of exactly what we're doing when we do a hypothesis test. And I know it's possibly still confusing, so let's walk through a nice example. Let's take an example from the textbook. So example 9.6, the average weekly earnings for women in managerial and professional positions is $670. Do men in the same position have average weekly earnings that are higher than those for women? So this is a one-tailed test. We're going to look at the average earnings for men, and we're asking, are they higher than those for women? So I'm writing a number for in place of mu sub 0. I could also write it on the margin like this, and I could say mu sub 0 is equal to 670. So mu sub 0 is always a number. We just have to look through the problem statement to figure out what that number is. Okay, so this is our alternative hypothesis, and our null hypothesis has to be the same but with an equal sign. All right, so that is what we are wondering about. That is the question on our minds. Do men earn more than this than women, or do men earn more than $670 a week? Okay, so how are we going to now test this? We have to do a sample. We have to take a sample, so we're going to take a random sample. Somebody's done that work for us, and they found that X bar is $725, so the sample mean is $725. The standard deviation for the sample is $102, and the sample size is 40. And this is a large sample. Remember, we had to assume large sample so that the central limit theorem would work for us. And large sample in continuous problems, measuring problems, means that n is greater than 30. Okay, so we have the sample size, and now we also want to test this hypothesis at a significance level of 0.01. So we only want a 1% chance of making an error, making the particular error that we're going to reject the null hypothesis when it's true. Okay, so that is all the information that we need. There's really 1, 2, 3, 4, 5 numbers in this problem, and we just need to kind of slot them into the right place. And now we need to take our steps. So next step is to calculate the Z statistic. And so it is X bar minus mu sub 0, which is a number, so we'll just fill it in right away. And we're going to divide that by the standard error, which is standard deviation divided by the square root of 40. Okay, and so X sub 0 is 725. And we do all this calculating with the correct order of operations. I'm just going to put some brackets in to help remind me what that order of operations is. And we're going to get 3.41. Okay, so that looks high. That looks high for a Z value. We usually, we called outliers anything bigger than 2 early on in the textbook, but 3 is certainly pretty high. 3.4 is very high, but is it too high? And so that's where we use now the alpha is 0.01. The situation is exactly like the drawing I made in the previous, but let me do it again. Oops, that shouldn't be. Anyway, it's something like that. Here is 2.33. There is alpha equals 0.01, and this is 0.95 probability there. And so our test statistic is at 3.41. That is in the rejection region. Remember, the acceptance region always contains a Z0. Sorry. Acceptance. Okay, so our Z statistic is in the rejection region. That means we reject the null hypothesis. And so we finally need to write a conclusion in ordinary words. So we're going to say that the average wages for men are higher those for women in managerial and professional positions. Probability of error is, instead of that, we can often say we are 99% confident. Okay, so that is a complete test of hypothesis for that situation. So we have walked through it now, and we're going to look at a two-tailed example, which is actually a little bit harder to understand. So let's say we want to do the same question, but now our alternative hypothesis is that men's earning are different from those of women. The null hypothesis will still be the same. So different here, and over here we're saying greater than. So these two problems are actually rather distinct. If we're trying to figure out whether men earn more than women, then we use the greater than symbol. You look in the problem statement for, does it say more than? Does it say greater than? Does it say bigger than? Does it say larger than? Does it have that kind of language? Whereas in this example here that I'm doing, all I'm changing is that I'm wondering whether men earn something that's different from that of women. And so that's usually the word that you'll see in that kind of a problem, different. And this problem is different. It is distinct from the previous one. So you do have to be careful. And this one actually is a little bit harder to establish. And we're going to see why right now. So all the calculations are the same. The test statistic will be 3.41. So it'll be exactly the same value, exactly the same formulas. What is different, though, is the critical values in the rejection region. So in the case of the two-tailed test, we have 99% in here. And so that means there's 1% that's not in the hump in the middle. but it has to be distributed equally between these two tails. So a two-tailed test, there are two tails which form the rejection region, and it's not 1% anymore, but this is going to be 0.5%. Oops, it's not 0.5%, that's 5%. I'll fix that. So 0.5% here and 0.5% there. So you look up the Z value corresponding to 0.005, and it's about 2.58. It's not exactly, but that's the value that we usually use. It's 2.58. You'll see this in the table, in the formula sheet. You'll also see it in tables in the textbook. And you should almost have this number memorized at this point. They're so commonly used, this few numbers. So, the chance of us incorrectly rejecting the null hypothesis, so if our Z is here or here and it's actually true, the chance of us incorrectly rejecting it is now 1%, but it's distributed evenly between 1% for incorrectly rejecting because it's too high and 1% because it's too low. Our Z value, I mean. So in this case, our Z value is again 3.41. It's still in the rejection region. So this is reject. This is reject. This is accept. So our test statistic falls in the rejection region, and we reject the null hypothesis. That's what reject means. It always refers to the null hypothesis. So we're going to reject the null hypothesis, and we're going to draw our conclusion. In this case, watch, the conclusion is different. Conclusion that men's wages, men's wages are different from those of women in managerial, professional positions. Okay, say this with 99% confidence. Okay, the key here is different. That was the hypothesis that we're testing, and so that is what we have to follow through with. Different is the word. Notice that in the conclusion previous was that I said that they were higher. So it really is distinct, a two-tailed test versus a one-tailed test. Sometimes they're very similar, and it's actually easier to do a one-tailed test than it is to do a two-tailed test. The numbers are not so bad. So remember, the critical value for one-tailed in this example was 2.33. The critical value for two-tailed was 2.58. So it's sort of easier to be in the rejection region. In in the first case. But you can't fool around with this. This is a big statistics no-no to change, from a two-tailed test to a one-tailed test, because the one-tailed test is easier. It happens, unfortunately, often, but it's something that is I don't know what you might call it. It's so bad it might even be called academic misconduct. So you've got to decide whether you're going to do a two-tailed test or a one-tailed test at the very beginning of your investigation before you gather any data at all. You can't make that decision after you've gathered the data. So it's really a question of, what do I want to know? Am I interested in whether they're different, or am I interested in whether one is greater than the other? And so, and once you've made that decision, then you have to do the correct test for the decision that you've made. But you can't change your mind after you've gathered the data. You can't change your mind partway through the investigation. You have to have the question in mind before you do anything. So that is an outline of large sample statistical test for the population mean, test of hypothesis for population mean. There is another example, 9.7 in the textbook. It pretty much follows what I just did, so you can go ahead and take a look at that. It's a little bit different. What they're doing in 9.7 is the only thing that they're really changing. I mean, the whole problem is different, but the main feature that's different is that they're using an alpha of 0.05, and it's a two-tailed test. So what we do is split alpha in two, and I'm going to draw my picture like I love to do. These pictures just are very rough. They don't have to be accurate, but I find them extremely helpful. And so here is 0.025, so 2.5% there, 2.5% here, and that's 95% in the middle. So this is our acceptance region. Always contains 0, a z value of 0. That's messy. I'll fix that. Okay. 0. This is acceptance region. And this is rejection region. This is also rejection region. This is a critical value. And we're going to write that critical value with a symbol Z sub alpha over 2. I think I'll write it up here. Z sub alpha over 2. And this is negative Z sub alpha over 2. So everything's symmetric. Just erase this. It wasn't quite right. So everything is symmetric. That means that our critical values, one is positive, the other is negative. The symbol that I use for the critical value is Z sub alpha over 2 for a two-tailed test. For a one-tailed test, the critical values are Z sub alpha. And so the Z sub alpha over 2 in this case is our familiar friend 1.96 would be the critical value, and this would be negative 1.96. So that gives the location for this boundary. Right, so that's what changes in the example 9.7 in the textbook. That's the salient difference between what I just gave to you and example 9.7. So in general, we're going to find that there are a number of important critical values. So our significance level, we have four popular choices for significance level. Sometimes we divide it by 2 and sometimes we don't. But if we do, it's easy calculation to make. And the critical values in each case you can obtain from drawing the diagram that I gave you, or you can just look them up in. You can just look them up in the table in my formula sheet. Let's see, we've done a few of them already. So Z sub alpha over 2 in this case is 1.96. That's very familiar to us. If this one was 2.58, this one was 2.33, and this one is 1.645. The Z sub alpha's corresponding values are very similar, so it's kind of easy to get confused when you do use the table for this. You've got to be very clear on whether you're doing a one-tailed test or a two-tailed test. But notice that hang on a second here. And I said it's easy to get confused, and I just got confused. So let me try to sort this out here. All right, I'm going to leave this table for now. You can look it up in the formula sheet. I just don't want to write numbers that are a mistake here. So you look them up in the formula sheet and figure out what those Z sub alphas should be. All right, so that's just, this table is to spare you from having to do a lookup in the standard normal table over and over and over again. These commonly used values for alpha turn into commonly used values for the critical value Z sub alpha over 2. So I'll leave you the task of completing that table for Z sub alpha. All right, so that is the kind of big picture. There's a nice table in the textbook, and my copy of the textbook on page 365. There is a kind of outline of how to do the statistical test of hypothesis, and the condition, of course, the assumption is that it's a large sample, so n is greater than or equal to 30. And that is sort of the way to do it. Now, there's one other issue. That is the p-value for the statistical test. This is another major issue. And so this is maybe a little more complicated. So unfortunately, we're kind of heaping up the complications in this section, but let's just plow into this. So suppose I got a Z statistic that was equal to 1.645. How much probability is in this tail? It is a 5% probability then in this tail. And so in that case, the p-value, it would be 5%. So the p-value is the smallest value of alpha for which the null hypothesis can be rejected. And it has a very specific meaning. It is the actual risk of rejecting right. So it's different from setting our confidence level in advance. We might set our confidence level in advance to be, well, whatever, 95% to 99%. That means our significance level is 5% or 1%. And then we accept or reject based on that. But in this case, what we're doing is we are calculating RZ. We are then determining the actual risk, which is the probability in this tail. And in this particular example, it was 5%, but it can be any number. It can be actually any number at all. So it kind of gives more information. The p-value gives not only the Z statistic, but it gives this area, this probability of the actual risk of rejecting the null hypothesis when it's true. And so it kind of provides us with more information. So it's very common in papers, in journals, and so on to quote the p-value. If you write a journal article, you have to compute p-values. Another benefit of the p-value is hard to explain at this point, but I'll say it anyway. It's that some statistics are Z statistics. Later on, we're going to see T statistics. We're going to see F statistics. We're going to see a whole whack, and there's actually a whole whack of them. There's like maybe 10,000 different statistics. So it's hard to know in your have this all in your head about what is significant, what is what the critical values are, and we'll see that even for T and F, it's hard to know what the critical values are. You'd have to memorize entire pages of numbers. So instead, we quote the p-value, which is a kind of a more universal thing. It's kind of universally understood what p-value means. It's the actual risk of rejecting the null hypothesis when it is true. So that means no matter what test we do, the p-value kind of means the same thing for every statistical test on Earth. Whereas the Z is not comparable to a T, which is not comparable to an F. They're all got different critical values. So that's why that's really the reason why I think p-value is so important. So how do we calculate the p-value? Well, let's go back to our friend here. Let's see if that's a good one. All right, so we're going to go back to our friend. Oops. This one-tailed test of hypothesis. So if you remember, this was example from the textbook. This was example, which example was this? This was example 9.6. So example 9.6 in the textbook, we go through this, we calculated the Z value. Okay, so here is our graph. Here's the critical value. We see that this Z value falls in the rejection region. That means we're going to reject the null hypothesis. But what I'm going to do now is calculate the corresponding p-value, which is this probability, which is a little bit bigger than 3.41. So I'm going to look up in my table the Z value of 3.41, that is 0.9997. So So that means that the area under this curve is 99.97%. That means that the area under the tail is 0.03%. And that is the p-value. So to determine the p-value, Z statistic in the normal table and then determine how much probability is in the tail. And this is for one-tailed tests. For two-tailed tests, it is actually, unfortunately, slightly more complicated. So let's do the p-value for the corresponding two-tailed test. So remember we had the negative 2.58, 2.58. This was our rejection region. It still came within the rejection region. But what we do is a little strange, and there's good reasons for it, but I don't want to go into all the details. I have to make everything symmetric in the two-tailed situation. So I have to find the mirror image of this. It's at negative 3.41. And now I'm going to add these two tails, these two probabilities up. So we've already calculated that this one is 0.0003. So this one is mirror image. It also has to be 0.0003. And so in this case, the p-value is 0.0006. So in general, the p-value for two-tailed is twice as large as for one-tailed. So we just calculate it as if it were one-tailed, and then we double it. So that's how we calculated a p-value for our two-tailed test. All right, so that is kind of a lot to remember. It's a little bit tricky, but that is largely it. Now, we can do the test without even mentioning the Z statistic. So we just look at the p-value. So p-value version of the test of hypothesis test is where we compare the p-value to alpha. And so that if the p-value is less than alpha, then that is reject. If the p-value is bigger than alpha, we accept. So if you're a researcher, you like to see small p-values. And very often we have alpha is 5%. So a significant discovery, statistically significant, means p-value is less than 0. Is less than 5%. That's what significant means. And we can also introduce some other terminology. If alpha is 0.01, 1%, then highly significant means the p-value is less than 1%. So you get to pull out this terminology and use it. Even if your journal sets this as the standard, you can still throw in, oh yes, it's highly significant because it's less than 1%. Yeah, so that's a nice thing when you can do it. It sort of establishes the actual probability of making an error of the type we've been talking about is now only 1%. So this is better. Having a small p-value is a smaller probability of making an error, which is better. So that is a p-value approach. You might be asked to calculate p-values and then compare p-value to alpha. That is what we mean by the p-value approach for these problems. All right. Finally, one last thing in this section. This is that there are two types of errors in statistics. So we can make up a little table, and so our decision is either to reject the null hypothesis or to accept the null hypothesis. But it may be true or it may be false. And so if we accept a true null hypothesis, we've made a correct decision and everything's fine. And if we reject a false null hypothesis, we've also made a correct decision. And everything again is fine. In this corner here, we're rejecting a true null hypothesis. This is the error that we've been talking about. This is called a type 1 error. And so the probability of a type 1 error is under control, and it is this number alpha. Now, unfortunately, there's another kind of error that we could make. That's where we accept a false null hypothesis. And we haven't talked about that kind of error until now. There's a symbol for the probability of a type 2 error, and that is beta. Now, unfortunately, beta is actually really hard for us to calculate, so I'm just going to avoid getting into this. This is more advanced, really, material and statistics, so I'm not going to go into any detail about how to calculate beta, but you just should know that it exists. And quantity 1 minus alpha is confidence. The quantity 1 minus beta is what we call power. It's the power of a statistical test. So we know how to control alpha. We just decide at the beginning what we want alpha to be. We can't make it 0, but we can make it 5%, 1%, whatever. Controlling beta is a much harder thing to do. But it is very important, and this is where a lot of, say, research on statistics is, and a lot of more advanced statistics is to control beta and try to increase the power of our statistical tests. So, I just wanted to mention that because you should know about the concept, how um, that it exists. To calculate beta is very hard. You really have to use computers to do it anyway. So I'm not going to go into any detail about that. There is a blurb in the textbook on my copy of the textbook, the fourth edition. You'll find this on page 370 to 372. It is a very difficult section of the textbook. So don't do it unless you're confident about everything else. Do all the problems, the normal problems, and then you go ahead and read up on beta if you're really interested in this. But I'm not going to put it on the test. I'm not going to put it on the final exam. All right, so that is it. This has been a long haul for us, so I'm going to sign off now and take a bit of a rest, and then I'll come back and do the rest of chapter 9 tomorrow and post it tomorrow. All right, so you should now try the problem set. Try the problem sets, first half of the chapter 9 problem set. And I'm also going to post some supplementary exercises from the textbook to the Your Courses site. So you should try as many problems as you can. That's how you're going to get good at this. It can seem really confusing the first time you run through it. So the only thing that's going to untangle your mind is for you to actually do problems and a whole bunch of problems. Do the problems until you feel confident with them. That's how you're going to succeed at this. All right, so that's it for now. We'll